Assalamualaikum and hello everyone. So this is your second last lectures, right? Lecture 6, thermodynamic analysis of a process. Okay, right. So the objective of this lecture is to present a procedure for analysis of practical processes from thermodynamic points of view. Okay, right. So real irreversible process are amenable to thermodynamics analysis. Okay. And then the goal of such analysis is to determine how efficient energy is used and produced and to show quantitatively the effect of inefficiency in each step of a process. And the cost of energy is a concern for manufacturing industries. And the first step is to attempt to reduce energy requirements, right? So that if you reduce the energy requirements, then you will reduce the energy costs, okay, right? So this in this case is that we need to look at the irreversibility of the process. The treatment here is limited to steady state flow processes because of their predominance in the industrial practices. Okay, right? As everybody knows that most of the processes, okay, right, is in steady state because in steady state that you can control the process easily and there will be less variables, so we can the changes in the variables, so we can calculate. Yeah. Okay, for many processes consists of number of steps. The loss work calculation are then made for each process step separately. Okay, that so we have seen this equation before, which is the work of loss work is due to the surrounding temperature and the entropy of generations. And and then for a single surrounding temperature, right, the temperature surrounding that, then we can get the total loss to this, okay, right, the total entropy generations. And everybody know that entropy generation is always positive, right? It can be zero if you see uh, 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 reversible process, and then irreversible will be positive. It cannot be negative, right? Everybody know that. Okay. And then by dividing these two, okay, right, so we can remove the temperature, and then from this, okay, right, then we can know the ratio here, and then from equation 5.31 that the summation of loss work is equal to the work due to the actual work, no, the actual work minus the ideal work. Okay, so the actual work is actually the ideal work plus the sum of the losses of the system. So this is this is what we can calculate, right? In the ideals, when the ideal gas or ideal liquid, okay, right? Then we can calculate it, and then we need to find the losses, and these losses is what we can calculate to the actual. Okay, right? But for overproducing processes, okay, right? The actual and the ideal are negative, so we will have the summations here. Okay, I mean, we make it positive because it cannot be okay, right? Because the ideal cannot be negative. Okay, right? So if let's say this the actual is bigger and the losses will be always be positive, so it become a negative. So that cannot be. Okay. Okay, these are examples here. Okay, in these examples, we have uh, power steam cycles here. Okay, right? So we have a pump here. Pump, we compress the vapors into liquid. Okay, right? So this is over here is a subcooled liquid, and then enter the furnace where it heat up from subcooled into saturated until it's superheated. Right? So when it come out here, it's superheated. So this is the property here. And then in turbine here, it's changed the phase into convert the heat into work. So we will expect the drop in pressure. Okay, right? So in over here, the wet vapor, the X is at 0.93.78, and then this is the temperature. Okay, right? The temperature has been reduced. Okay, right? And then condenser is to remove the heats. Okay, right? The further heats to the surrounding at 25 degrees Celsius. So this is the data. Okay, right? And then in the okay, right, so in the furnace here they use methane. Okay, right, so methane and air, Okay, right, methane and 2 mole of oxygen reproduce 1 mole of carbon dioxide and water. Okay, right, but okay, so from the table in the appendix, table C4, then we can get the enthalpy generations at 25 degrees Celsius. Okay, right? So this you can calculate that, and also this is the Gibbs energy. Okay, right? We can calculate from the table also. So from here, then we can find what is the entropy, right, at that temperature here. But we know that the process, the combustion is done at 35% excess air. So you can see here is 2 mole here times 1.25. So this is the percentage, the extra mole of oxygen. So we got 2.5 mole. So this 2.5 mole times the nitrogen here. Okay, even though nitrogen does not help in the combustions, but because of the existence, it might absorb the heat from the when it been during the combustion process. So we cannot ignore the nitrogen's molecules in the combustion. So the total mole of air is 11.905 mole of air. Okay. After complete combustion and methane, the flue gas content. Okay, so we can calculate this. Correct? This is the number of mole. 1 mole of CO2, water. This is the extra oxygens, right? I mean, because it has extra 25% more. Correct? And then this is the nitrogen. Okay, so this is the value from here. Okay. Correct? So this is the mole fractions. Correct? And then from this, we can rewrite into this form here. Okay, first will be the air. We can mix it at 25 degrees Celsius into oxygen and nitrogen, and this is the methane. And then this oxygen will react with this methane, the standard reaction at 25 degrees Celsius, and then it produce 1 mole of CO2, water, and oxygen. And then nitrogen does not involve any in the combustions. So, and then we mix it together, all of this component, and increase the heat. This is at the standard condition, and then we increase the heat to 460 degree Kelvin, and then produce 12.905 mole. Okay, right? So if you draw this kind of processes, it's very much easier to analyze it later. Okay, for emitting the air, okay, right? So we find what is the A enthalpy and A entropy here, right? You can calculate using these formulas, correct? And then for step B, okay, right? What's step B? This is step B, right? The oxygens from air and the methane. Okay, right? So we can find what is the entropy is, and also the entropy. And then for C, this process here, we mix all of these components. Okay, right? So C, this is the summation here. Okay, right? The enthalpy is 0. Okay, right? And then the entropy is 90.510 joule per Kelvin. And then for B, for the heating up process, okay, so we can get this data from table C1. Okay, for all these components here, this is at constant pressure. Okay, heat capacity at constant enthalpy, and this is capacity at constant entropy. Okay, from this, we can calculate the total. Okay, is about 401.52. Okay, this done with number of molecules, from here. Okay. And then we find that CPS is 400. And then from here, then we can calculate what's the enthalpy for part D and the entropy for part D. Okay, right? So this is the value. And then for the total process of basis of 1 mole methane burn, the enthalpy is this, right? The summation. All we need to sum all the enthalpy here, right? For all the processes, it's minus 737,639 joule. And it's the same also for the entropy, and then it come out for 208.186 joule per Kelvin. Thus, this is the enthalpy for the uh, enthalpy and the entropy. Okay, since that the steam rate, okay, from the previous example, it rated as 84.75 kilogram per second. So from this energy balance, now we can find what is the number of mole of methane, which is 366.30 mole per second. So the ideal work is, right, the number of mole. Okay, so we use the previous equation, right, 5.2, and then with this, and then we gather the ideal work is 292.94, 292,000 90 940 watts kilowatts. Okay, so the rate of generation of each of the 4 unit power plant is calculated. Okay, right? So we can calculate, and the loss work is given by equation 5.34. Okay, right? So for the furnace, okay, we find what is delta G is. Okay, so and then okay, Fs is the flowing fluid. We find delta G for the furnace is 583.12 kilokelvin, and the work loss is, we use this equation here, and then that is 175.05 thousand kilowatt. And then we do the same for turbine, and then we find this is the losses, and then we do it again for condenser. Okay, right? Which also been determined in the previous example in chapter 8. Okay, right? So we find this. Q is minus 1, 0.2, and then the entropy generation is 41.69 kilowatt per Kelvin, and work loss is 12.32 thousand kilowatt. Okay, for the pump, is 0.74, and the work loss is 0.22 thousand kilowatt. Okay, right. So the entropy generation, we need to list it down like this, and then we calculate it to the percentage. So this divided by that, and then work from 100. So a work analysis is carried out using the previous equation whatever developed at the beginning. Okay, right? And this, the result on this analysis, and then we got this work. Okay, right? This is the actual work, and this is the losses. Okay, right? So the ideal is 292.94 thousand, yeah, kilowatt. Okay, from here we can see that most of the work losses is from the furnace. Okay, right? Okay. And then the thermodynamic efficiency of the plant is 27.3%. Okay, so this is the percentage of the ideal work. Right? And the measures of efficiency is from furnace or boiler. So you guys, you can see it here. So we can break it down into the processes, and then we analyze it part by parts. Okay, right? From this part here, then we can identify where the inefficiency come from. So the highest for this system is from the furnace or boiler, which is 59.8. So there's a few things that we can do to improve this. Number one would be to insulate, okay, right? To insulate the furnace or the boiler, okay, right? Reduce the leakage of steam generation, right, in the boiler, and so on. With that, we can improve it significantly. The rest of the system is quite good, even for the turbine, right? The losses is only about 8.6%, less than 10%. Condenser is good, pump is also good. Okay, the example number 2 is a linear system, is to liquefy methane, yeah, methane gas into liquid. Okay, so we look at the process first. So the first process is the compression here. Where did it compress? Okay, when it compress, right, from vapor to liquid, then you need to remove the excess heat. Okay, so this is the Q. Okay, right? So the Q is been removed, and then you go to the heat exchanger here. But somehow in the heat exchanger, we get some um, uh, heat leakage into the system. There's about plus 5 kilojoules, and then go to the throttles. Okay, the purpose of the throttle is to spray it back, right? Convert it back to, not all, but those in a stable form will be in a liquid form. Okay, just like your hairspray, right? The hairspray is in liquid form, but when you spray to your hair, some vapor is stable already in the liquid form. It will drop down. Okay, right? So it will maintain in the liquid form. Okay, so that is the purpose of this throttle valve. But some for the unliquefied methane will be recycled bags. Okay. Okay, to find the fractions of methane that is liquefied, okay, Z, you can calculate using the energy balance, okay, right? So this is, where is it? H4 here, okay, this H4 plus this should equal to that, okay, or this, This will be better because this, right? So this H4Z plus 6 minus 2 equal to Q, okay, right? So Q is the length from the surrounding with Z, which is 5 just now. So from this, we can find the fraction for the liquefaction, which is only about 4%, okay, right? 4.86%, very little, okay, right? Okay. And this result may compare with the value of 0.05 obtained in example for the set operating concept, but no leak. Okay, right. So if no leak, then this will be 0, right? So we will get a much higher percentage, right? Okay. Okay, so at this point here, okay, right? So all these point here, you can get list all the data, okay, right? One is superheated, okay, right? And the temperature, pressure, enthalpy, and the entropy, okay, right? For all this point here. Okay, this is the way that can solve the problem part by parts. Okay, point 1 to point 2, 1 for point 2, you can see that. Okay, the temperature is still the same, but the pressure have been increased, right? So the enthalpy also decrease and the entropy also decrease. And 2 to 3, okay, right? The heat transfer, okay, right? So you can see here the temperature will be reduced, okay, right? And then pressure is maintained, enthalpy, entropy reduced, okay, so forth, so on. So the work depends on the overall changes in the maintain passing through the liquefier. So we can use this work is actually this delta H minus T and entropy here, okay, right? This for the flowing stream, okay, right? So we get all this data and multiply that, we got it 53.8, okay? So all the stream, okay, right? And the rate on Trump generation and loss for each of the newest step of the process is calculated equation 5.33 and 5.34. Okay, right? So for the compression Q, we find what is Q here, and entropy generation here, okay, right? And then from here, then we can find the work loss, okay, right? Is the temperature, compression is that 300, and then the entropy here, okay? It's a T tau delta S generation, right? And then we do the same again for the heat exchanger, right? Which is 0.3879, and then the work load is 114, and the throttle also do the same thing, okay, right? So this is the ratio, right? And then 5, right? Some will go here, some over there, so it's a different conditions, okay, right? Because over here is in a liquid form, and this is in a vapor form. All right. Okay. Okay, right. So the work loss is 451 here, and then we can list it down. Generation, cooling, and compression, and this. Okay, this is 3.1539, and then percentage is here. Okay, right. So you can see here the entropy generations, and then the work analysis, right? And then for what we have calculated, overall is 1000. You plus all of this is the actual, and then the percentage is this. So we can see that the largest occur during the throttling process, right? The throttle 45%, and then followed by the compression. Okay, right? So replacing the high reversible process by turbine result in a considerable increase in efficiency. Okay, so that's why it's very common if they have a throttle process, they will use turbine because the turbine will generate energy will be used for compression. Okay, so with this, the energy from the throttling will be connected to the compression. So that will reduce the energy added to the compressions. That's how we can improve that. Okay, so that's why it's very common. If you go to power generation, you can see that they have a turbine, right? Steam turbine will be connected to the compressor. Okay. Okay, right. So for further reading, please go to your books. Right? For my old books, right? It's a chapter. My old books is chapter 15, right? Thermodynamic analysis of the steady state flow process. Okay, that's it for today. So thank you very much and have a good day.